kind of is. It's home built, essentially. It was actually built by our Society of Physics students a few years ago. So, we can debate how much we trust them to have done a good job, that it's safe and everything. I'll leave that up to you to decide how safe you think it is. But basically what it is, it's a giant vacuum chamber. And inside, there is a small, what we call spherical capacitor that generates a very strong electric field to then accelerate atoms that are inside of it, or nuclei, really. Okay? And if they get accelerated enough, they can collide with one another and ultimately fuse together. That's the goal. That's why it's called a fusor. In fact, there are plans for this. If you look online, people can build this in their garage. It's really usually not so dangerous, as we'll see. Okay. Any questions so far? This is kind of just for fun, so. Okay, so the idea, let me just do a little bit of board physics before we actually do the demonstration. So the idea behind it, again, is that we're trying to get nuclei to come together close enough together that they can fuse. Okay? But nuclei of atoms are positively charged. We've already learned this. And in fact, what's in this one right now is deuterium. Okay? So it's mostly vacuum with a little bit of deuterium gas. Okay? So what is deuterium? Deuterium is just hydrogen with an extra neutron. Okay, so hydrogen atom, that's the lightest element, 1 proton, 1 electron. But deuterium is 1 proton, 1 neutron in the nucleus, and 1 electron. So we can calculate, it's actually pretty straightforward. We can calculate how much energy we need to get these to come together in the first place. So if you have, like, let's say one proton, we'll just ignore the neutron for now. It's just tacking along, carrying some extra mass. But we want 2 protons to come together with such speed that they can get within a certain distance. And that distance they need to get within is actually the radius of the nucleus. So that needs to be, so this is initial. So final will be final, and this distance d is about 1 times 10 to the minus 15 meters, so 1 femtometer. Okay, so an atom, just for a rough order of magnitude, an atom is about an angstrom, or at least a hydrogen atom. That's about 10 to the minus 10 meters. So the nucleus of an atom is 5 orders of magnitude smaller. So this, if you've ever heard atoms are mostly empty space, this is why. Okay, so 5 orders of magnitude smaller for the nucleus within the atom, and then the size of the atom is essentially defined by the orbits of the electrons around the nucleus. Okay, so positively charged, so we want them to come together. So you imagine they start at infinity with some velocity. So we'll just say they have the same, right? So they have some kinetic energy. And then as they come together, right, they're interacting electrostatically so they're going to slow down because they repel until they reach a stopping point. So if I write down my energy equation, conservation of energy, so delta K plus delta U equals 0, right? U. Okay, so the kinetic energy is going to be K final minus K initial, and again, plus delta U equals 0. So I'm going to say K final is 0. So they come all the way, and then they slow down, and eventually stop. And I need that stopping point to be within this distance. Because the reason for that, at that distance, the scale of the nucleus, a different force takes over, something called the strong nuclear force. So the strong nuclear force, so whereas electrostatically they're repelling, the strong nuclear force will dominate at that scale and cause them to fuse together. So I'm saying K final is 0. So then I need my initial kinetic energy to equal whatever my change in potential energy is for these. Okay? And the potential energy is just, I mean, these are point charges. I can treat them like point charges. So the potential energies is Q times V. So Q times delta V. So that's electrostatic potential energy. It's charge times electrostatic potential. And then that's going to be Q times 1 over 4 pi epsilon naught. Another Q over R. Or in this case, I guess, T equals T. So, and the Q is just the charge on the proton, so I'm just going to call that E. That's my constant E. My fundamental unit of charge, so I'll just say this is E squared. Okay. So 1.6 times 10 to the minus 19. Okay. So I need to, in order to get this to work, I need to impart this much energy, to get fusion to occur, this much energy to the system. So where is that going to come from? So we're going to create an electric field inside of this. And that electric field is what's going to give the energy to the protons, or nuclei, in order to accelerate them. All right, so now we need to know something about the actual physical design. So what's inside of there is something called a spherical capacitor. So the idea is essentially you have a sphere made of water. So it's actually tungsten, I think. So it's like a cage, actually. So it's not completely, it's not solid, but the wire is kind of it's like a cage. And then at the center, we have another small cage. And so these get charged up in an opposite way such that there's a strong electric field between them. So you get minus Q on the inside one and plus Q on the outside cage. And then that's why we call it a spherical capacitor. Because you have two equal and opposite charges separated by some distance, and it creates an electric field between them. So you get some electric field E. Okay, and we can use, so when we're outside the cage, right, it's essentially neutral, right, because they are plus and minus, and so the net charge is 0, and we know by Gauss's law, the electric field integrated over the surface tells us about the charge inside. So if there's no net charge inside, then there should be roughly no electric field out there, given as long as it's symmetric. Actually, it doesn't have to be symmetric, sorry. Okay, but inside the outer cage, right, then if we draw a Gaussian surface in here, then what matters is this minus Q in the middle, on that smaller cage inside. And so we know we can treat, by Gauss's law, that was one of the first examples we looked at, we know we can treat that like a point charge. So then let me write down the electric potential in this case. So V for the inside is just going to be minus Q, 1 over 4 pi epsilon naught, minus Q over R. That's my electric potential. Actually, no, let me write the field. Let me write it as the field first. Okay. So then it's R squared R hat. All right, so now we inject deuterium into this vacuum. And so you have these deuterium atoms, and as soon as they get anywhere near this electric field or inside this cage, the electron is quickly stripped off, because the energy is high enough that it ionizes the gas. So now we can, and then the electron will go, I guess it'll maybe run into the outermost cage because it's positively charged. Okay. And actually you'll see it glow. But then, so the protons, or deuterons, as they're called actually, the proton and neutron, are what's left. Okay. And now they're under the presence of this electric field. They get attracted to the center because they're positively charged. but they're going to, they have some velocity, they get sped up. So they don't, at least often, they don't crash into the center. Instead, they just keep on going through. So you get, so it's attracted, it speeds up, goes through the center, and then slows down again as it goes through the other side until it reaches zero speed, and then it's attracted back to the center, and so on and so on and so on. So they start orbiting. So you get these orbits of these protons. I'll just write, or deuterons. I'll just write P cross to indicate that. And again, this is where the fusion comes in. If they have enough energy in these orbits, when they run, they will at some time run into each other and then fuse. That's the goal. Okay, so we can figure out their energy. We can just say, like, integrate from the outermost cage to the innermost to figure out, integrate the electric field to figure out how much energy they get. Yeah, so delta B minus integral of E dot dl. So E points towards the center, and I'm going to say, I want to ask how much energy does it get as it moves to the center, so E and dl point in the same direction. And so then this just becomes integral of E dl, which then is, so I have my 1 over 4 pi epsilon naught, integral of epsilon naught minus Q over R squared. Actually, I already took care of the minus sign in here, okay, in the direction of R hat. So when I said E points along the same as dl, that's accounting for the minus charge, because I'm saying the field points in. And we actually already did this, I forgot, and then it becomes dr. We already did this in class in the very beginning when we introduced electric potential. It ends up being something like 4 pi epsilon naught, 1 over R final minus 1 over R initial. Something like this. So this tells us how much energy that the proton gets as it accelerates towards the center in this electric field. Okay, so I can take this is the energy that the electric field gives, and I can set it equal to the energy that I need in order to get them to the protons to come close enough together. And actually, you could say this is the total kinetic energy, so each proton needs a half of this. So then I'm basically saying something like 1/2, 1 over 4 pi epsilon naught, E squared of D equals Q over 4 pi epsilon naught, 1 over RF minus 1 over RI. And so this spherical capacitor, so this is my, just to be clear, this is going to be my RF. This is my RI. I think I probably lost a sign somewhere. I think I should still have a negative sign. We're just talking about magnitudes. So whatever that is, I think we'll look inside there. I think it's on the order of maybe this is a couple centimeters and this is maybe 10 centimeters or so. So you can, we're not going to do it, but you can plug those numbers in and you can figure out how strong the electric field needs to be, and therefore what potential electrical potential you need to put into the system. And the answer ends up being that the voltage is about 10,000 volts. So we have to get that spherical capacitor up to about 10,000 volts in order to have any hope of achieving fusion of these ions. Okay. Any questions so far? Okay. Let me think. Is there anything? Oh, yeah. Before we look at it, so Greco loves this glow strip. So instead of doing something fun over the weekend, he wrote a program. So and then kindly provided it to us. So just briefly, so what the program is doing, what that he wrote is doing is it's creating an electric field for these, modeling the electric field for this spherical capacitor, and then tracking 2 protons in the presence of this field. So he's got, so like this is his, so this is his potential, electric potential, so that's the 10,000. These are the radii of the inner and outer spheres of this spherical capacitor, and then he's got the proton 1 and proton 2 he creates, and then tracks them over time in the presence of the electric field. So let's just run it. So this is what it looks like. And so below, what it's doing is it's tracking the distance between, and I just realized he misspelled separation, but not a big deal. The distance between them, so you see they never get very close actually. I assume this is in meters, and we need them to get to 10 to the minus 15. It looks like they're getting to about 10 to the minus 2 maybe, so like 1 centimeter, so not close enough for fusion, at least in this program. But you can see kind of the orbits they're tracing out. So you see the outermost sphere of the spherical capacitor and then the innermost one. So remember, the outermost one is charged positive, the innermost one is charged negative, and so the protons are orbiting. Why I can't rotate it? Oh, there we go. Yeah. I don't know. It's kind of looking. You get this nice pattern that develops. I don't know if I would have spent my weekend making this, but anyway, we get to benefit from Greco's efforts. So that's kind of your conceptual picture of what's going on inside of here. So again, just to reiterate, it's mostly vacuum. You have this spherical capacitor charged up plus and minus Q on each side, or minus Q on the inside, plus Q on the outside, such that the electric field within that is on the order of 10,000 or thousands of volts. And that's enough to accelerate the deuterons, well, to strip off the electrons and then accelerate the deuterons. They're orbiting this thing at very, very high speeds, and then occasionally they'll run into each other and fuse. Okay, so like I said, this is in some ways the, very, very coarsely speaking, the same process that powers both thermonuclear weapons and stars for that matter. In reality here, we're probably, Greco said, he estimates that we're probably getting like 1 fusion event per day or per week maybe. So really, it's not happening often, but at least in principle, it can happen within this chain. At least we hope it's not too long. Okay. Any questions before I turn it off? Yes?
How do catalysts change things? Because I know there are certain catalysts that result in a higher output versus input.
Okay, that's a good question that I don't know off the top of my head. I mean, the idea of a catalyst, right, is it accelerates the reaction without being used up itself. I don't know what sorts of catalysts would be used in this. Yeah, probably strange metals that maybe will give off neutrons or some. Yeah, I don't know. Well, the energy has to come from somewhere, though. I mean, if you. Yeah, I don't know. What might use to accelerate this? Any other questions?
That way we never get these test results back.
You're recording because you think I might electrocute myself, right? So, hopefully not, right? It's very old equipment, right? We got this. I get really nervous when I see things like this that are like 60 years old or something. You don't know how. Huh? Should maybe more reliable. That could. Yeah. All right. I'm gonna flip it on. Okay. Nothing happened. I'm gonna turn up the voltage. Okay. So far so good. Nothing's happening, or at least
Yeah, the one up front.
Greco didn't tell me there was a limit. So
That's a great question.
What is it?
Yeah, he did turn the lights up too. Okay. Okay, so something's happening. So, okay. So the electric field is created. So the voltage is on. It's supplying power. The electric field is created in this spherical capacitor in there, and it starts to glow. And the glow is, again, it's from I think at least it's from the electrons being stripped off and then being or actually, yeah, it's the electrons get stripped off, and then sometimes when they go outside the field, they recombine with the nuclei, and then when the electron recombines with the nucleus, it releases a photon. So I think that's what it glows from. Okay, so I'm gonna turn the lights off, and then so we're basically about done. Just a reminder, if you came in a little late, we're gonna make a clicker question, so you get credit for coming today. Just make sure to put in a response. I'm gonna turn the lights down, and then give everybody a chance to come up and take a look at this. And what I want you to do is, you can look, yeah, you can see it in here, in this viewport, or you can look from underneath and see it. This one's a little bigger, so you might get a little better view. I'm going to kindly ask that you do not touch it. I mean, it's pretty safe. Yeah, okay. No, Greco said the ground wasn't so good in the lab, so then the cart got a little bit electrified too, but it seems okay now. Okay, but still, don't touch it. In particular, this Dixie cup here, this is the most critical part, because if you touch underneath here, you might get a shock. Okay. So we really want you to be really careful. But you can come up, take a look inside, see the glow, and maybe take a picture of something. So let me turn the lights.
I like get a response, but I can't. It says I can't go on.
Let me turn off.
Come on.
Okay. Yeah, so thanks everybody for coming. I'll be very quick. Yeah, there's a viewport down here. I don't know if it's quite as good. More people.
What are the bombs?
Oh,
yeah.
Oh, wow.
That's so cool.
There's a purple on this side too.
Yeah.
Yeah, so this is the spherical capacitor. So there's a small cage on one side and a large